So for this example, we're going to use the data from the student-athlete example earlier and a 95% confidence interval to find the margin of error for the mean number of hours required to spend on athletic activities by all student-athletes in the conference. Assume the population standard deviation is 2.3 hours, and we want to see how many student-athletes must be included in the sample to be 95% confident within a half hour. So again, for that first part, we're not going to see problems like this too often, but I do want to show you how this works at least once so you get a sense of what's to come when we're making these kinds of computations, where I will say that this can be done in the calculator, but because, like I said, I'm not emphasizing this, I'm not going to make a whole video on that, even though you'll at least see what it looks like here. Anyway, if we want to make this value, we need to get our margin of error. That's just a matter of recognizing what we have and what we need. Where first, we need to think about what our sample size is. Because remember, we're looking about this in terms of something like the central limit theorem, where here we have that our sample size is 40, as we talked about before, which is definitely bigger than 30, so I'm not going to write it, but the central limit theorem does hold, and that means that everything we want to do works. More often than not, the central limit theorem is going to hold because I'm more interested in seeing you get practice with this process than tricking you. So you can assume that's going to happen most of the time, but it's still good to be sure and remind yourself of just how important that result is. But anyway, we have n equals 40, and from here we want to find the z-score, that is our critical value. Where to find that critical value, we want to bear in mind that since our level of confidence here, C, is 95%, that is 0.95, it means we have 0.025 in each tail. And if we have 0.025 in each tail, I'm not going to draw the distribution here because it's kind of cheating to draw a distribution for this, but that would mean we want the critical values to come from having 2.5 in the ends. And I already talked about this earlier, but that 95% in the middle is an important value. So when you see a lot, that corresponds to critical values of form plus or minus 1.96. So this is our critical value, and then from there, let's just bear in mind that we're given sigma is 2.3 in this case. So if we want to find E, we just have to put all that together. We have that E is equal to the critical values, or usually we take the top one when we're making this margin because we want it to be positive. So 1.96 multiplied by 2.3 over the square root of the sample size, which here is 40. Multiply that out, take the square root, estimate it, and you'll get that the margin of error is about 0.7. So if we want to be 95% confident of getting the actual mean amount of time spent, we would want our margin of error to be about 0.7 of an hour. And then from there, if we want to make our interval, we would add and subtract that 0.7 from x bar and get an appropriate window. But for our second question, we want to figure out how much we would need in order to get the margin of error E to be 0.5. So for E equals, not 0.5, excuse me, for E to be equal to just 1/2 hour, it's too many zeros. There's a lot of zeros in these problems. What we would need then is our value N has to be, again, still we're talking for a 95% confidence interval, 1.96 multiplied by the value sigma, 2.3, divided by our current goal for the margin of error, 0.5, and that 5's having some trouble again, and then we square the whole thing, which tells us that we need about 81.29 to get that value, where whenever we're talking about this thing, remember that value n is a number of subjects, a number of trials, a number of things, a discrete value. And whenever we have a discrete value, any fraction has to get rounded up. So if we wanted to be within that 1/2 hour with a 95% confidence interval, we'd need about 82 students in our sample. We're actually going to see, as we're going through here, that those sample sizes don't need to be quite as big as you might expect, depending on what level of accuracy you're looking for. But anyway, this is about all we're going to see for 6.1. Like I said, the assumption here that we somehow know sigma but don't know mu is a bit unreasonable. So next we're going to move into 6.2, where we're going to talk about what happens when we know neither sigma nor mu, and we have to make our way with something else. In particular, we're going to look at a construction called the t-distribution.